Okay. All right. So today we're just going to review for the exam, no new material, and we'll just do that the first half, then we'll go downstairs and use the second half to finish up project 2, which I'm sure you're all very close to finishing, right? One caveat here that I'm going to warn you guys about, because I know many of you, very few of you, I think this is your first semester, but many of you are in a situation where this is your first engineering course. And if you haven't noticed yet, it turns out engineering courses tend to take way more effort than not engineering courses. And one of the things that has me concerned right now is that I think for the last homework that was actually due, right, we have 2 homeworks out that aren't due until Sunday night or Monday or something. But for the one that was due, I think only 8 of you turned it in. And so now I'm doing a review, which for 8 of you is a review, and for 12 of you is not really, right? So my warning is, going forward, what you're going to find out on this exam probably the hard way is if you haven't done the work and prepared for it, then the review is kind of like, oh, I was supposed to know that, oops, instead of kind of polishing the material that you don't understand, right? Because if you come in knowing what you don't understand yet, then you can ask me good questions. Without that, you have to just ride along with whatever I'm prepared, right? So I ask you in the future, not just this class, it's not for my class, but for the final exam and for your future and for your own sanity, try and do the homeworks when they're due, because it will save you pain in the future. It's just a better way to study. That being said, let's go ahead and get started. And basically all I've done, I printed out some of the homeworks, and I actually printed out for myself to reference, and then I lost it, and I'll pull it up. The actual exam that I used last year, which is I'm going to use kind of as a guide to remind myself what we need to study. As far as what we need to know is VHDL, right? That's one of the main things that we've learned since the last exam. Most of the content is since the last exam. So that means VHDL, latches, flip-flops, and then state machines. And the state machines, we don't need to know anything more than we talked about last time. And there's homework to help you practice it. I will post the homeworks even before it's due, right? This homework is not, you're going to have access to the answers. My recommendation again is strongly do the homework before you look at the answers. Don't trick yourself into thinking you know it by following along with the answers, right? Because that's not understanding, that's being good at copying. And you're going to trick yourself into being confident for the exam when you actually have no idea how to do the process. So I will post the answers hopefully tomorrow or Friday so that you'll have at least the weekend to review. But don't look at them until you've tried the homework. Okay, sorry. I'll pull this up so I make sure. That I get this correct. Sorry, it's just been a load of technology problems recently. There we go. Okay. So the things I want to be specific about for VHDL, you're not going to be expected really to be able to write perfect VHDL handwritten, right? That's kind of unreasonable because we've learned how to write VHDL with these tools that kind of give you error checking. However, you are expected to know it conceptually. So let's say that I have an exam question, and it could be as simple as given Okay. Given this picture, write the entity that must exist for U0. Now, I'm not expecting perfect punctuation, right? But I am expecting you to understand the concept of what's the job of the entity, right? You should know that. And a different question is, I could say that given just this picture, write a port map for me, or write a component declaration for me, or write structural code, assuming that these components have already been declared for you, right? I can give you a picture that's just a block diagram, and you should know all of those different things. So let's talk about, why do I know them? Well, in the case of the entity for VHDL, the entity describes what the outside world is going to see. The label on it says what it is. So I know in the case of U0 that it's going to have entity U0, and you might at this point go, is there an is there a, I don't really care, right? That's one of those kind of technical things that I'm not going to look after, but we're going to know that, okay, I know there's this port thing, and in those ports, I know it's going to need an A and a B that are both inputs is a reasonable, right? If it's on the left, it's probably an input. If it's on the right, it's probably an output. If it's on the top or the bottom, we probably have to guess, or I'll give you an arrow, right? It will be clear. If it's on the left, it's an input. If it's on the right, it's an output. Top or bottom, I will try and give you an arrow, unless it's a component that you already know what it is, like a full adder, right? I'll give a full adder on the bottom. There's something labeled C, especially CI. You know, it's a carry in, right? Anyways, then we have to just know our ports. We can assume that they're standard logic vectors. Guess what? If you write SLV, I'm totally okay, because I do it all the time. You're allowed to do it, because it's just about communicating that you know things, not about taking up all of your time writing words, right? And then this is the really important part. This is 2 down to 0. Guess what? If you write the down arrow, guess what? I don't care, as long as you communicate that you understand. Technically, right, if I really cared, there's a semicolon there. You figure that semicolon, again, don't care. Next, we have C as a type output. It's 1 bit. That means it's going to be standard logic. And I'm done, right? That's my entity. And I would need, well, not quite. We need the space that we know that we end entity. And guess what? I don't care if you write end entity down here, or if you, right? Either one, right? As long as it's just communicating the idea that you know there needs to be an end there. If you forget if it's end entity or end the name of the entity, either one is okay. So I'm just hammering home is the concept of what is an entity doing in its general structure that I'm looking out for. Then if I say, give me the component declaration, that means I need you to know what a component declaration is, right? And the component declaration is really as simple as right? We just copy and paste, make it a component, we're done. Then if I take it further, and a good question is, given this picture, assume that I've created the component declarations for me, write the remaining code to make this, write the structural code, assuming that I have created for you the components. Okay, so that means we're going to treat it kind of like a test bench. We have no signals created. Or if I'm nice, I would do something like this. In fact, this is probably even a better question. Yeah, This is actually an excellent question. A, B, C, D, E, F, G, H, I. I don't really care what the signal name, and we're going to call this component U2. Okay, so I will say, assume that I have created the entity U2 for you and declared the components for you. I've done the component declarations. Write the rest of the structural code to build this. Okay, so that requires that we understand what the entity does. It requires to understand the entity has made H, I, and we're going to call that J for us, right? Those signals exist. I don't have to declare them. And so now it's just a matter of looking at, well, if the components are already declared, what other code do I actually need in order to make this work? Well, the mistake would be to jump into the begin, right? Because that's not what we want. What we want to do is we're missing something before the begin. What am I missing before the begin? The signal. I need that. So I would need to do something like signal int s is standard logic, right? Because it's not created for me. Then the next step is I need the port maps, right? So I'm going to do something like give it a name, and this is roughly what I want to do. So we're going to say, I don't know, call it component 1, or component 0 is probably better, is a type U0, right? Name type. It would be a mistake to call it U0 is U0, right? It doesn't like if your name is the name of a component cannot be the same as the type of component. That'll be an error, right? We need different. So component 0 is U0, and it has a port map. Again, don't really mind. And I will expect you to use explicit port mapping. I do not want to see positional port mapping, okay? Which says that there is a port A that gets mapped to signal H. Right? Make sure there are things that I do want to see, okay? That you want to try your best to get right, which is like the mapping signals that we use all the time and the assignment statements. I do expect you to know the difference between equal, that equal, and the assignment, right? The types of things that you're going to use a lot, I expect you to know. I expect you to understand the difference between or and plus. I expect you to know that you can't go C equals A plus B if the types are standard logic vectors, right? We can't do that. That's the kind of thing that I want you to know. The syntax of it, specifically like forgetting semicolons, forgetting parentheses, that kind of thing is okay, right? That's the difference. So I want to see this port map AH, B gets mapped to I, and C gets mapped to int S. Which maybe I need to go back and label that int S, right? The things that I don't really care about, right? If you forget the semicolon there, totally fine. I'm probably okay if you do a semicolon there instead of colon, right? If you make that mistake, that's minor enough that I don't really care. Anyways, then we go comp 1 is going to be of type U1. It's going to need a port map. And we look at it and say its ports are D. It's mapped to int S. E gets mapped to J. And now here's an interesting problem. This is the most difficult part of this. What do I do now? Yeah. Yes, so there are two fully good ways to do it, and this one is totally fine. So the first way is we realize that, oh, I need a concatenation. So let's create a new signal, something like, right, these would be underneath, but this is actually okay code, F signal and G signal. And each of those are standard logics. Oh, I need the word sig here, right? I forgot that. So sig FSGS. Or I could recognize that all of these are the same type and say sig int FSGS, since are all standard logics, right? Minor change, realize that I needed new signals. Then inside of the begin, I can say that, well, I have here, so I'm going to port map F to the F signal and G to the G signal. And then say E, F, G, H, I, J, I guess that makes this K. Then we say, well, K is simply FS and GS. Right, that works. The other option involves this section of the map, where I could just say F gets mapped to K at 0 and G gets mapped to K at 1. Right, that's totally it. Either one works, both are right. Just make sure that you understand some way of doing it. Right, that's all this is testing, is to make sure that when you and your partner were working in lab and you had a couple of pictures that one of you understands this, I want to make sure that you both understand this, right? I want to make sure we're not skating through on someone else's labor, and it will reveal itself in the exam. So that's all I'm testing, is the structural code here. Yeah.
So because we did the projects together, should we just take the exam together?
Yeah, there you go. No.
Right.
Anyways, I do want you to understand structural code and the basic idea of VHDL. Another question, and I will actually do this. We'll do it at the end. I'll pull it up. I always ask a question where I'm going to put VHDL code that you should be able to understand what it is. Sometimes this means I post up a project or something similar to the project, or something like an 8-bit adder, and I test it and make sure it works. And then I go in and I make like 8 errors in it. And then I post it and ask you, and what the question is, find 5 or something like that. Or I make 7 and ask you to find 5. Because I want you to be able to identify the problems with the VHDL. Most of the problems are going to be functional problems, right? Or sorry, syntax problems at this point. The final exam, I asked functional more than syntax, a better mix. Most of the mistakes that I will introduce in the code are going to be syntax. Some of what I introduce will be conceptually wrong, right? So I would that's a good syntax error, right? If I just left off the underscore S, that kind of thing. The port mapping would be a good functional error, like if I didn't assign an internal signal and I just assumed something was there, that kind of thing. But we'll go through an example at the end of this once I figure out how to make the projector play nice. Okay.
I have a question.
Yeah.
On the exam, will you name signals or will we have to name them?
Some combination of that I want you to recognize. Like here, it's like this is a good question where I just wouldn't, and I would make you go assign something and then name it. Another question, take a moment, think about it. What is the difference between a flip-flop and a latch? Take a moment. I want everyone to take a moment and think about it. Difference between a flip-flop and a latch. Yes. Yes. Which one's clocked? Flip-flop. Flip-flops have a clock, meaning they react to the edge of a signal, whereas right latches don't. That's the big difference between them. What is the difference between sequential logic and combinational logic? Think about it. There's lots of differences, it turns out. So think about good examples of what is the difference between sequential and combinational. All right, who's got a difference?
Sequential logic has memory, so it depends on what has been inputted before.
Yes, sequential logic can have memory, technically can have memory. We haven't delved enough in it that I probably wouldn't be that picky on an exam, but yeah. Not all sequential logic has to have memory, but it can, whereas combinational doesn't. Different, something else that differs.
You say like sequential logic depends on what happened before.
Another way of saying that is the order matters for sequential logic, whereas combinational doesn't. Combinational doesn't matter if I put this before the component declarations, right? That's combinational logic, because this can go here. Whereas sequential logic, the order that I put things in, think of a test bench, right? Do this, then this, then this. That's sequential. Order matters. It doesn't just pick it. Combinational doesn't care.
So that should be sequential logic, and then like when you're just making like just doing the HDL for I don't know, like the ALU, would it be conditional logic?
Maybe kind of. The test bench is not the only place that you'll see sequential logic, right? Flip-flops are sequential as well.
Okay. It's like if something happens, then this is gonna happen.
The big key is if there's the word process. If it's inside of a process, it's sequential. And I want to say something now. I don't really test on this. You can technically design combinational logic using a process. I don't really talk about it in this class because it just confuses, but I do want you to know that it's not like this big gap in my knowledge. If you go find out and read someone building sequential or combinational logic with the processing, Dr. Gardner didn't tell me this. I know. It's just more confusing than it needs to be. Yeah.
So what is another, like, what's an example that you've shown us in class in combination?
A full ladder, right? And in the case of a full ladder, we have those two equations that one calculates the sum and one calculates the carry out. The order of those don't matter. If I put the carry out equals this, or is assigned to this, and sum is assigned to that, and flip those around, it doesn't care which the order of those are. Yeah. So basically the full first half of the class was all combinational. Okay. Speaking of full ladders, what is a less than ideal property that makes it so that we can't build very large adders as the ripple carry adder, the way that we've built the adders before? You go for it. You haven't done it yet. Time delays, right? Gate delays is it just takes a long time for ripple carry adders to actually finish computing the number once they get really large.
If they get too large, like by the time this number starts changing, this number hasn't changed.
Exactly. Yeah. By the time, if you make them too long and you update the inputs, it ripples through slowly, and it's possible to change the inputs before that carry goes all the way through. You'll never actually see the right answer.
Is ripple carry adder, is that what we made in the project?
Yes.
Okay.
Yeah. Ripple carry adder is actually the only kind of adder that we talk about. That we've talked about in this class. If you watch like my last year's lectures or something, I've talked about other kinds, but I've tried to narrow this down and kind of focus on the basics, and then 3610 we'll go talk about more in depth. But yeah, the ripple carry adder is what we've used throughout. Okay, so here I'm just actually going to pull up some examples. which homework is this? Homework from the chapter 12 homework. The next big one is I do expect you guys to be able to do timing diagrams, both with like combinational logic and with sequential logic. So things with flip-flops and things with combinations. In fact, we can combine them, right? We could put a little bit of a combination in them to see what happens. It won't be very complicated as we go through, and by the final, we might get some more complicated logic, but make sure that you understand the major types of flip-flops that we talked about and latches. So SR latch, D flip-flop, JK flip-flop, T flip-flop. Right? Those are your big ones, basically. And when I was in lecture, right, and we threw up I went through and I actually did a timing diagram for this. What is this device? It's an SR latch, right? That's another good question. I could draw this, ask you what it is, that kind of thing. I could also ask you, like, if I call that Q and this S and this R, I could say use a timing diagram to prove to me that this will set or reset when they are asserted, right? And then I would just give you a blank timing diagram and we would go ahead and you would make some assumption like, let's start assuming that S is 1 and R is 0 and see what happens. And then we'll change S from 1 to 0 and write what happens. And then we'll change R from 0 to 1 and see what happens, right? And I could do that kind of process. There are other types that your book talks about, other ways to build SR latches besides the NOR gate version. That would be a good one because I haven't done it in front of the class yet, but it's the same steps. It's the same idea. It's just proving that you understand the concept and aren't just parroting what I wrote on the board, right? Yeah. Yeah, absolutely. I think this board is getting worse at being erased as this semester goes on. Okay, so what we're going to do is there's no clock, so we can just get right to set and reset. And if you just start with an assumption, and in fact here, what we want to do is it turns out it's easiest if I assume that either set or reset starts out asserted, because if neither of them starts out asserted, what we find out is we don't know. We don't know what the condition is, because remember that if they're both 0, it just holds the previous value. So if we understand that about the SR latch, and we understand that I don't know what's in there right now, and I don't know what's in there, I don't know what's in there until I set or reset. So we can go ahead and say, let's go ahead and set, turn up. I should use a different color. So we'll start setting, we'll stop setting and stay. We won't be resetting. We'll wait a little while and then we'll start resetting. Okay. So then let's go ahead and just follow through what happens. Well, in the case of a NOR gate, my NOR gate is really S and Q, right? That's this output. So if I call this signal just Q bar, because that's what it is, that means that Q bar is that. And this operation is NOR, right? So Q bar is S nor Q, is all this is saying. And so we say, well, a NOR gate, simply, an OR gate would be 0, 1, 1, 1. So a NOR gate is 1, 0, 0, 0, right? And now I just say, well, that means that if set is 1, the only option is for it to be 0. Okay, so that makes Q 0. It doesn't, my point here is it doesn't matter that we don't know what Q is. Q is unknown, doesn't matter. That's why starting with set or reset high is so good, is because it puts it in a known state. Okay, then I say, well, if that's true, then Q bar is, as long as set is 1, then Q bar is 1 or 0. And so I'll draw that up to there and be like, okay, it's 0. And now I say, well, at this point when set is 0 and reset is 0, I kind of have to know what Q is in order for it to matter, because if Q changes, it changes. So let's just go to Q here and see what happens. Well, Q is the NOR of not Q nor R, right? So not Q, if not Q is 0, then, which is, well, I said R is 0, so that's the easier one. So if R is 0, then we could draw the truth table, which is the same. Right? Where Q is Q naught nor R. So now we can go ahead and say, well, what does that mean for Q? Well, R is 0, not Q is 0, right? So we're looking at the 0, 0. That means we must be 1. Which is good, right? Because Q bar and Q should be opposites. They are. Feeling pretty good about we're on the right track. Now when S drops to 0, we actually have Q and Q bar defined. And now we can go, okay, what happens? Well, in the case of Q, which is R nor Q bar, then we say, well, Q bar is 0 and R is 0, so Q stays 1. And it's not going to change until something else happens, right? It's going to stay fixed because they're defined. Then the next thing that happens here is, well, we could verify that Q bar stays the same, right? We can either take the shortcut and we know that, or we could look out and say, well, Q bar is just defined as S nor Q, right? Which is S is 0 and Q is 1. So that would put us here on that K map, and we'd have 0 still. So 0, 0. Then the reset happens. Now my Q bar, or Q rather, has reset. Reset goes to 1. We no longer care what the other input is. It's just reset. So that means that the reset is asserted. Q drops to 0. And then we can check and Q bar goes to 1. That's all. Yeah.
I was just wondering with timing, because the reset, like the reset comes, just we have reset once.
Yeah.
It's gonna turn Q to 0.
Reset is 1, turns Q to 0, yes.
And then so like in the diagram, as far as timing, it would take a little bit for that Q to go up and change Q naught to 1, right? So
Yeah. It takes a little bit. I'm not going to be that picky generally on the timing unless I explicitly call your attention to it. I just have the habit of drawing a little bits of delay because as you've noticed with the flip-flops, if the delay's not there, it turns out it's harder to do the timing diagrams than if they are. But anyways, if you don't have those little bits of delay, unless I call out the delay, it's okay. In general, in this class, you can kind of assume ideal devices unless I'm asking questions about delays. Okay. Let me do some erasing.
We're gonna have the same amount of time as last time or more.
Correct. It'll be the same. So it'll be an hour 15, and then we'll transition to lecture. Actually, I think next time. Yeah.
I don't know where you're going, but will there be things on like bouncing and de-bouncing?
Not any more than is on the homework. So the exams come from the homework, the labs, and the lecture a little bit, but mostly homework and labs is where most of the exam questions come from. So we only did a little bit with debouncing. We'll get more into debouncing coming up actually when we actually have to design with it in a lab sim. Oh yeah. More timing diagrams. There's gonna be a lot of timing diagrams on this one. And by a lot, I mean just several, maybe 3. You all have the benefit that I'll provide diagrams for you so you don't have to sit and draw them. There is, just so you know, on my exams, I very often just reuse other timing diagrams that I've used before, like as far as the number of blank lines. So your timing diagrams won't necessarily have the right number of lines. Don't freak out. Okay, so let's say that we have the easiest of all flip-flops to be flip-flop, right? That means that I need a clock and I need a D for data input. And let's make it a complicated one that has an enable. Right? Okay, so then we say, let's start out enabled. I'm going to turn off here. I'm going to turn on there, and I'm done. And then my clock is just going to do this. And then data. Back you. Go ahead, take a moment, fill it out. I'll start filling it out in a minute or two. Yeah. Assume nothing. I'll give you some dashed lines to help. Someone actually asked me a really good question today via email. which is the answer ended up being that is all you really need to know. If I don't specify, right, there's no obvious indication of whether this is rising or falling edge triggered device until I add those dashed lines. Because of the way that we teach, in fact, every university teaches it, you just assume it's rising edge triggered unless otherwise specified. If it's not specified, it's rising edge. If I want it to be falling edge, a common way, and you'll see this in the homework, is that I put an arrow for the trigger. This is not falling edge, so let's just do it as rising edge. If you're done and already waiting, go ahead and just start drawing yourself another timing diagram with a couple of with some clocks on it, because we'll do another one after this. In fact, I'll start drawing another one for myself. Okay, are we ready if I start answering? Okay. Where does Q start? We don't know, right? Which either way, if you write a U or an X, I'm okay. X is kind of the way that we draw it, but the Votto simulation would give it U, right? Wouldn't know. Until that rising edge. And if we're enabled and data is 1 on a rising edge, that makes us 1. And we know that it's not going to change until there, right? Until the next rising edge, until something important happens. In this case, that's rising edges. Then it's a matter of, well, it's still 1. And in the case of a D flip-flop, it stays 1. It just pulls that in. Well, now there's another rising edge off here that sees the 0, right? And we're enabled. So it's going to drop to 0. Here we have a rising edge, but we don't care. I have no interest in what happens, right? So until enable is on, nothing's going to change because that's just what these flip-flops do, right? Now here's the tricky one. What happens next? We don't know, because if I turn it on at the same time as a rising edge, there's a question of, well, I'm enabled here and D is 1, right? So it turns out that it could either stay disabled and keep being 0 or become enabled and take the 1. So we don't know. A funny thing happens if I do this enable with if D was 0 at this point in time, then the enable is kind of in this weird state of, well, whether it's enabled or not, it's a 0, right? But the issue is that depending on the architecture of this D flip-flop, right, you have that kind of chasing its own tail situation. And the way they enable is we still actually don't know. So forever changing an input signal at the same time as the rising edge, just say, we don't know. Because weird things are gonna happen, right? That's basically the answer. So until there's another rising edge while we're enabled, I don't know. Then once this happens, now we can pull in the 0 and we're 0 again.
So it still takes the 0 off of what it was before you didn't know? Like it,
Yeah. So so this don't know is because it could be this one or this 0 held, and then we come 0 here because of enable and 0 and rising edge. Right, and this is not uncommon. If I were to ask the kind of situation of like there's 2 different ways I could ask this, right, with delays and without delays. Let's suppose, just real quick, that I did this and I didn't specify there was a problem, then we're okay, right? Because enable isn't on yet. And there's this, so it's not don't care, it just holds the 0. But then the question I could ask if I did it this way is, what non-ideal property of the flip-flop could cause you problems in this situation? Not the synchronicity. What's the name for the non-ideality here?
You're saying like why you're getting those X's, right?
Well, so let's suppose that this is the timing diagram where there's, and I'll draw this since you're further back to make it obvious. That's the correct timing diagram. You fill this out. And then the part B of the question says, what property might you find, this is another way to get it, what property might you find on a data sheet that could cause you problems in this situation? At this is too far really to call this, right? At this point in time, what property have we discussed in class that might cause issues? The setup time, because I didn't leave enough time before this change, right? So we need to remember setup time, hold time, and clock to queue delay.
Setup time, that's how long it takes it to rise.
How long a signal should be stable? Oh, this is hold time, isn't it? Sorry, because let's just draw it. So if this is clock, the time before the rising edge of the clock is TSU, and the time that we need to be stable afterwards is hold. We need you to be stable before the clock and hold afterwards. So in this case, we didn't hold for very long afterwards. Hold time violation. And then obviously clock to queue doesn't play an error in this one, but we've talked about the clock to queue delay problems that can occur in like a counter, right?
So you're just saying because there's such a short delay that the hold wasn't like, that there wasn't enough.
That there might not be enough, yeah. Yeah, so the question that I phrased is, what property might be the problem here? Ends the hold. And there are technically like other properties that could come into play that we just haven't talked about them yet. Because technically, like I could say, well, clock jitter. If this bounces around, that's a problem. We haven't really talked about clock jitter yet, other than kind of in passing, right? So I don't expect that answer. I expect setup time, hold time, clock to queue delay. Those are the non-ideal properties of flip-flops that I want you to be interested in for now. Then some dashed lines. Take a moment. Answer that one. This little thing I got here, I'm indicating that Q is starting at 1 in this case. Okay, let's talk about this one and see what happens, right? In the case of the JK flip-flop, what happens when there's a rising edge, right? Nothing is going to happen until that rising edge. What happens when J and K are both 1? So it toggles. Yeah. So don't forget JK 000110111, and we just say it's the next Q, right? Is stay the last Q if we're 0, reset, set, or toggle the last Q. Just flip whatever we were, right? So that means J and K are both 1. So that means at this point in time, it's going to toggle, which is drop to 0, right? And here we're still toggling. That means we're going to jump to 1. Next rising edge, J is 0, K is 1. When K is 1, that says set to 0. So reset, right? Again, we don't care what happens until the next rising edge. During that rising edge, they're both 0. So what does that mean it is? Stay the same, which is 0. Next one is J is 1, K is 0, which is 1. 0, 0. Stay the same. And 1, 0, with J being the 1. 1. There we go. JK flip-flop timing diagram. Right, JKs are the hardest. They're the most complicated. So the hardest thing that I could do is something like the next question that I'm going to go through, which is I've taken 2 T flip-flops and I genuinely have no idea what's going to happen on this one. I could think about it for 3 seconds, but I haven't yet and figure it out. But I'm going to have a toggle signal which says, sorry, I'll stay out of the way for this if you're still right. The toggle signal says if it's a 1, we toggle the input, right? Then we have a clock with an inverted clock, which makes this device effectively a falling edge triggered device, right? That's going to look at the input here. So a question that I could ask for this one is, what assumption do I need to make about this circuit in order to make a successful timing diagram? It has to start at a value, yes. Yeah, I have to assume that Q is something, right? And that is unique to T flip-flops in that in the JK flip-flop, if I don't start at a value, it will eventually become a value, right? It'll eventually become defined if I assert either just J or just K. But with a T flip-flop, if I leave it undefined at the beginning, it will never resolve into a value. Make sense? So I've assumed, and I've just written not Q because I didn't use Q. This would be a silly trick, right? That ultimately doesn't matter. Is if I did this and I gave you enough lines, you may end up filling out what does Q do, and then you just write Q as the Q bar is the opposite of Q, right? As is, if we see it and go, oh, well, Q doesn't matter, I'm just going to write Q bar. So in the question, this one might say, assume that Q starts at 0. Well, that means Q bar 1. And then we just say, well, the only thing that this first T flip-flop can do is toggle. But if I call this T2, right, as the input to the next one, T2 is only true if T is true and not Q is true. We'll see if anything happens, right? Because it might not, and we'll just do a couple and step through. So when we start out at that first rising edge, toggle is true and not Q is true. So the AND gate is true. So T2 can be true. And here's what's kind of interesting. So here I would probably specify, assume a small gate delay and a small clock to Q delay to make this easy, basically. So it takes a little bit of time after the rising edge of the clock for Q bar to toggle like it's supposed to. Just takes a moment, and it's going to stay there and a little bit until the next toggle. And then I'm going to ignore T2 for a while, right? I'm just going to finish the output Q bar, and then I'll deal with T2 later because it doesn't matter, right? Okay, so Q bar says, well, let's toggle. Here, 0, don't toggle. Here, well, let's assume that I wasn't an idiot and I did that and made sure that there's enough time so that we don't go undefined for the rest of forever. So that makes this a toggle. That one toggles. That one toggles. That one doesn't. This one does. There we go. We've got the first step out of the way. Now we look at T2 and we understand that T2 is not Q and T. Yeah.
So Q will change every time T is on, or Q will toggle.
Yeah. So if I call this Q2, Q2 will toggle every time that there is a falling edge of the clock and T2 is true. But let's solve for T2 first before we even decide if we need to worry about Q2. Because there's a good chance that we might not, just because of the small delay, right? So let's go ahead and use red dashes for the falling edge. That's too close of a color. Let's use blue. I'll continue those dashes if it turns out that it matters. Let's go ahead and look at this. Well, T true 2 is looking at this falling edge. Is T true? Yes. And Q is not. So T2 then, when it starts out, T2 is combinational of Q, right? Not Q, and T. So it's the and of these two. So it does start out at 1, right? It starts out true. And then there's this rising edge of the clock that it responds to. So T2 drops as soon as Q drops, right? Because it's no longer and.
Does it have to?
T2 does not. T2 is not a clock process, right? That's the trick here, is that T2 is not clocked. T2, this is where we're combining the combinational and the sequential. This is like the hardest we're gonna get, essentially. Okay, so then when this rising edge happens, the Q is not gonna change, but let's worry about Q2 later, right? Let's finish T2 to see if we even need to draw Q2. Okay, so then T2 says, well, let's look at the next chance that we get, which is here, where we're true, and it becomes true and then stops being true right at that same time. Right? So T2 has changed here. That's really funny. So in order for me to make this a good question, let's go ahead and offset this a little bit, if you'll forgive me, so that it doesn't happen right at the same time. This is generally why I test my own exams before I don't want them to. There we go. Now, instead of dropping right at the edge, we can drop a little bit after the edge, and we can have like a circuit that does things. Then the next time we might be true is all the way over here. And it's really just this little bit of a blip.
So is it possible in an actual circuit that would never reach 1?
Oh, absolutely.
It takes time for ISO to rise and then start dropping.
Yeah. The next time I could possibly be true is here. and then I stop being true. I can't be true. I can be true. Okay, let me finish these blue dashes since it looks like it might actually matter a little bit. Oh, that didn't actually matter. That's okay. Okay, there we go. All right, so now we say that here's a falling edge where it's going to toggle. No toggle. Here's a falling edge where it's going to toggle, and that's it. So we are going to toggle twice. So then we go and we write out the Q2, and I would give you some assumption about Q2. Let's say Q2 starts at 0, right? And then you would say, well, Q2 goes from 0 to 1, stays 1, drops to 0, stays 0. I'm not going to write it for, right, that one's easy. Because I will take the exam before I give it to you, it will be on purpose if I end up going into undefined state.
So it would cause us to go undefined. Like you said, like if it's
Toggling at the same time as an edge.
and right, and, well,
Yeah,
right,
yeah. If I turn on my toggle at the same time there's a rising edge, I have a problem
just because you don't know.
because I don't know is it toggled or not
And then
toggled.
from there on, it just be undefined.
Now it's a random number as far as reality is
So
concerned.
to fix that in an actual circuit, would you need like a reset button?
You would need a reset.
That would basically set it either to 0
Correct.
or 1.
Yeah, and that's why we design resets into like all of our sequential circuits when we design VHDL, is so we can push the reset button and everything goes back to a known state. We know where everything is. Right. That's why you turn your phone off and on again if it starts being weird, is because that can happen in your phone where it gets into a weird spot, and just turning it off again and on again will put it back into a known state because they're designed that way, and everything's happy again. Okay, so that's like this concept. It might be a couple more circuits, right? Like I could do the clock enable circuits that we've talked about before and talk about, draw the output of this circuit based on the clock enable and such. At most, it's going to be a couple of flip-flops and a couple of gates. But there will be timing diagrams involving potentially D, JK, and T flip-flops, as well as SR and D type latches. Okay. Let's see what's next. My goodness, time goes by so fast in this class, by the way. Oh, you guys disagree. Okay, so the next thing that I have on my list that I want to make sure that you know is make sure that you are familiar with the devices that we've talked about in VHDL. So for example, if I ask you to write VHDL for a MUX, let's say I want, actually here, I'll just draw it. I could say, here's a two-part question. Part one, how many bits must, so I'm going to generalize. These are going to be I0 to I5, 0, 1, 2, 3, I4. And let's call this port S for select. First question, how many bits does the vector S have to be? Wrong. 3, right? Right. You know this.
Yeah.
3. It has 5 options, 3 bits.
And you just toss away all the extras.
Yes. Right. And we could write when others. I could ask, like, after you write this, what structure does this? What VHDL does this do? How do we build a mux? When else? Perfect. Right? So if I call this F, we say F is I0 when, sorry, this is really bad handwriting. Let me try again. When what? Perfect. Right, 3 bits. 3 bits. And then I would say else. And then I might ask, well, after doing the when else, what is a good else? X's. How many X's? How many X's? I know you know. Someone else. You know, I heard you right. 2. Because these are 2 bits. So else. Yeah, because we don't want to confuse the else, because the else is F is I0 or F is 2 X's. You don't want to confuse this else with the 3-bit S. Make sure we understand what's what, right? On the when else structure. Why? Why is this a good option? Exactly. It becomes obvious in your test bench if you accidentally put something wrong in this select, right? So another question that I could ask, if I had else I4, right? That was my last line. So I said it's I0 when 0, I1 when 1, I2 when 2, I3 when 3, else I4. Then I could ask, what happens? What is the value of F if S is 6? So if this is my code, so I0 when 0, I1 when 1, I2 when 2, I3 when 3, else I4. If I put 6 into S, what is the value, like the numbers, like
Whatever the
let's say that I put, we'll do this. Let's say I put that value into S. What is the value of F? It's I4, because that's what this else does. And so even though I put an invalid select in, I get a valid result, and now I have a problem, right? That's why the else X's is useful.
Usually you have 0, 0, 0, 0, 0, 1, 0, 0.
Correct.
0, 1, 0, 0.
Yeah.
1, 0, 1.
Yep. Yeah. So the other one I could ask, right? I could do this with constants like I had you guys do in the projects. And I would make sure that you understood what the constants were. So I might list the constant declarations and say when S equals some constant, and then ask what is the value of F, that kind of thing. I could ask you to, here is a 4-input mux in VHDL, use it to build an 8-input mux. Remember how to do this. You stick 2 of them together, you have a third one, you string them together, then it's just a matter of puzzling out the S's, right? That's another version of that structural VHDL that I talked about before, right? Just you have a mux, connect a bunch of them together. Done. I'm going to quickly, sorry, I've got to figure out the right way to do this, which is I want to pull up that code that I said I was going to do on the projector, but unfortunately I'm not set up yet. So give me like 2 minutes. Thank you. And after we do this problem, then we'll head down and do stuff. Unless you guys would rather review more, I could do that as well. I'll take a vote after I do this. Sorry, if I push this button, it's going to turn off the camera because they're the same frequency. And so I know it's really off. Nope, there it goes. Bye. Okay. Now it's just fucked up. Just because that's the Zoom is going to be unhappy. And actually, the Zoom will be okay. I'll switch it to shared screen or something, so that the Zoom people, if you review this on Zoom, you'll get a good look at the this. There we go. That should work just fine. And then I need to slide these out of the way and wander and turn off the lights. Okay, I'm gonna turn off the lights so we can see better. Okay, so the question here is, says there are 8 errors in the code below. Find and correct 6. They are all syntax errors, so you don't need to understand the purpose of the code to find them, right? So I've said, here's some code. You don't need to know what's happening because it's all syntax errors, right? It's all stuff that you should know. And so I'm going to scroll down just a little bit because I don't think there's any errors in the top parts.
Line 22.
Oh yeah, well, I'm going to scroll down to line 10 because that's, I think, where the first error happens. Because this allows me to zoom in a little bit more. And then unfortunately, I don't really have a good way of, actually, maybe I do. 1 second. Almost. Can you slide that? Yeah, thank you. That helps. Like some. Okay, so we're looking for, well, let's look for the 8 errors, right? To see the kind of things that I've done in order to do it. And I'm honest, part of the reason I do 8 is because in case I forget one, there's still 7. Because I forget how to count because sometimes I'm stupid and it's okay. So everything here is something that you've worked with before. It's just a new code, right? So there's a process with a sensitivity list. There's an if statement. We've done some if statements. I probably won't do an if statement for this one because I haven't done enough of them to ask that, I don't feel like yet. But I feel for example purposes, I think we're fine here. So good strategies. What would you start looking for? Semicolons. I like the idea of looking for semicolons because they're obvious and we can go be like, all right, we've got a semicolon. I'm missing, yes, line 17, no semicolon. That's a problem, right? Semicolon, semi. I think I got the rest of them are semicolons. Then we want to go and look at something like types. Again, I wouldn't do this to you because I don't teach Boolean really anymore. I just have you guys use standard logic vector. This one is a fun cheat that I do. But an obvious one here is with the data types, right? That's the next thing to look for, is make sure the type assignments are correct. This one's really obvious because here I've used the picks and here I haven't, and they're the same data type, so one of them is wrong. What else? What else is kind of common things that you guys make mistakes on? Spelling. Spelling is actually a perfectly reasonable one to go look and make sure that like the signals I've created are the signals that I've used. If I do those, I generally won't like mistype position. Like I won't just like drop an I out of the position. I'll like use a different signal. So it'll be at the very least only 2 characters. It'll be like the example I did earlier, where it's G_S versus G, right? I don't want to just hide it away. Other ones that are really good is checking the assignment statement versus the equal signs, right? This is actually correct. This use of equal signs. I wouldn't expect you to know that, but we would go through and make like, okay, so error is 1, error is 0, error is 0. Those assignments all look right. Here we go. I forgot the assignments down here. Nice. 2 of them, in fact, at the very bottom. Those are equals instead of assignments. And you know what a when else is, right? That's all it is. It's a when else that's done wrong. In fact, I did 2 of those.
That count as 2 mistakes.
It would in that case. We could look, we want to look at like the process. If I give you guys a process, which I might do, we want to make sure that the sensitivity list makes sense, right? So if for example, I built a D flip-flop or something, and I say in a comment, for example, that here's a synchronous reset, but reset is in the process. Is that right or wrong? It's wrong. Yeah, that's another example. The process is a good spot to look. Make sure that I didn't say the word clock instead of CLK, right? As I said, it should be at least 2 letters difference, which that is. Garage door. Let's see, I may need to scroll down a smidge. Right, we want to check that I have the end behavioral, end process, end ifs. Make sure that the else ifs don't have an E in them. Yeah. So I've got, let's double check. So I said we have missing semicolon is 1, 2, 3, 4. Are there any others that we found yet? So we're only up to 4. There's got to be more.
The before 100, the assignment is
Oh, there's,
Sorry, what line?
wrong. 28.
28. This is less than 100. This is a less than. Good. That's okay. We haven't delved into this yet, so I wouldn't. This is one of the labs, and so we had done this lab by the time I had this exam. We haven't done it yet here.
What about line 33, where it's position -1, or is that position -1?
Position -1, which here, right, you want to go make sure position is something like an integer that could be added.
On line 25, do you have to type out rising edge, or can you just write RE?
Line 25, you
Yeah.
say? You have to write it out. You have to write out rising edge. So good catch.
Nice.
Line 26 has an error. Who sees it? It needs a then. So there we go. Got 6. There's 2 more in here supposedly. I'm not perfect. There should be at least 1 more. Here it is. It's the entity, right? It's end garage door, not end entity.
Oh, no.
Right, I could do something, I could mess up these lines, I could have the wrong number of parentheses, I could miss out the data type, I could miss commas. It looks like I have all of those. I don't know what the 8th error is, but we found 7 of them. That's the kind of thing that you're looking for, mostly syntax. I might do one like mistake. It might include port maps instead of processes, or it might be flip-flops instead of the lab. It might be one of your old labs that I go mess up, but it'll be something like that.
So what if we find more than you ask for?
I don't do anything else, but it's okay because if you circle one that's wrong, I don't deduct points. So if you circle 7 of them and 2 of them are wrong, then you still got 5. No, because it is find and correct. So you would have to go here and you'd write semicolon. I do encourage you to circle them because I like to make sure that I find them. I mean, it's not an end world because you'll just, when I hand them back in the class that we hand them back, they'll come up and be like, here's this one that you didn't do. Yes, any other questions? Okay, yeah.
God, if there's that thing at the beginning again, can you make sure it's easy word instead of
No, it's gonna be worse. No, I'm gonna do something that I don't think any of you will know. Because I love seeing like the made up results. It's like my new favorite thing, and I'd like to thank you all for that. No, it'll be a word. It's just gonna be something obscure. How's your guys' Arab mythology? I'm currently reading like a book about Arab mythology, so maybe that'll.
Wow.
I know, it's not.
Books. I thought you were gonna say Egypt.
So I'll do this. Just point this out real quick. So here, this question, I don't want to show all of them because I might reuse a little bit, but this is name the device. It's an adder, it's a full adder. If you weren't really sure, because I switched it up and I use the XOR method, which is totally fine, it works. You could just do a truth table of what this does, because you'd see this hopefully and recognize its purpose, because it didn't change, and then you go, well, that's probably a full adder, right? And since I think I just did it in that device, it's a mux, right? Those are some of the questions that I might ask. In fact, did ask last year. This is literally last year's exam, or last semester's exam, rather.
Technically, that was last year.
What?
Technically, that was last year.
I'm faculty, I think, in school years. I feel like the only thing that I didn't address at all is like counters and shifters and encoders. So I might ask you like design an encoder that transitions from binary to like 3-bit binary to 3-bit gray code or something. Gray code. Right, which is if there's 3 bits, there's 3 different circuits that you just write K-maps for and solve. And then the other one that I didn't review was state machines, right? Which there are homework. Do those homeworks, email me if you have questions. It's going to be a sequence detector because we haven't done anything else, so I'm going to keep it easy, but I will put a sequence detector on there. Or something very similar, something as easy as this state, then this, with 1 input signal and up to 3 state variables, right? I'm not going to go over 4 potential variables. Yeah.
We're allowed to have our notes on.
Open notes, open book.
And if we have our notes on, you should be print them out.
Totally fine.
Oh, okay.
You can use the technology. I'll walk around. I have software that monitors the other sites. A bunch of different sites for my questions getting posted. There are answers to some of these questions online, and they are all wrong. And they're wrong in a very particular way. I did. Yes, there are lots of wrong answers on the internet. So don't trust them. In fact, I didn't even have to put all of them there because it turns out that people helping on the internet don't know anything. So take that for what it is. But anyways, all right. With that, I think we can go ahead and transition downstairs and finish up project 2 unless there's other questions.
Would it be possible for like this exam to be posted as like a practice exam?
I will post something. There's a few questions on here that I really like that I know aren't on the internet yet. And I also know that nobody in here is retaking the class, so they haven't had it before. So That they change. I change like numbers and details. It's just conceptual questions. And yeah, before you go ask your friends for the answers, be really careful because they got them all wrong too anyways. Last semester was a bad semester for this exam for some reason. You guys are you're doing much better.